Hi, ladies and gentlemen. This is Mr. Green again. This is another in my series of AP statistics videos that we're doing. We are looking at Unit 6, Lesson number 4, Study 1 and 2. I know, Lesson 6, Unit 6, you're going, well, what happened to all the others? Well, they're just continuations from last semester. Don't forget that. We are getting close to inferential statistics, so this is going to be the last lesson in Unit 6. We will be doing a review and moving on to the um, uh, test. So get ready for that. That's coming up here in the next couple times. So we are looking at sample distributions of sample proportions, and sample distribution of sample mean, and the central limit theorem. And we are actually taking those topics up directly this time. So if you toss a penny 20 times and record the number of heads, and calculate the proportion of heads and mark it on a dot plot on the board, what shape do you think that dot plot will have? Well, based upon the central limit theorem, this 20 times that you're doing it means that your sample size is considered large. And because of that, it's going to turn out to be a normal distribution. It would be approximately a normal. So the dot plot is a partial graph of the sampling distributions of all the sample proportions of size 20. If you found all the possible sample proportions, it would be a normal distribution, or would be approximately a normal distribution. Okay? So, is the sample distribution of possible values of a statistics from all possible samples and the sample size from the same population? Is the distribution of possible values of a statistics from all possible samples of the same size from a sample population? That's what a sampling distribution is. I know that's a weird statement. Basically, what I'm doing is I'm taking a sample, I'm taking another sample, I'm taking another sample. If I take all of them and they're all the same size, that's called a sampling distribution. In the case of the pennies, the distribution of all possible sample proportions, P. That's exactly what we're looking at. Okay? We'll use P for the population proportion and P hat for the sample proportion. There's a difference between them, okay? P hat is this particular sample that I'm looking at. P is the population proportion. And those are distinctly different. You just need to make certain you understand them. Now, suppose we have a population of 6 people. Alice, Ben, Charles, Denise, Edward, and Frank. What's the proportion of females? Well, it's 1 to 3. What is the parameter of interest in this population? Well, proportion of females. Draw samples of 2 from this population. How many different samples are possible? We could have Alice and each one of the other 5 people. That's 5 different samples. And then you could have Ben and the other 4 people. That's 4 more samples. That's 9. And then you could have Denise and 3 more samples. That's 12. And then you could have, that was Charles. Denise and 2 other people. That'd be 14. And then you could have Edward and Frank, and that'd be 15. Those would be your 15 different samples, and they'd look something like this. So let's look at this. If Alice and Ben is a 50%, it actually has 50% females in this sample, and Alice and Charles has 50%, and Alice Denise has 100%, but Alice and Edward has 50%, and Alice and Frank has 50%. Ben and Charles has 0%. Ben and Denise is 50, but Ben and Edward 0. You can see how we're getting the mean numbers of each one of these. So let's take all those and find the mean of all these means. Okay? And what do we get? Well, I think if you put them all together, you're going to get 1/3. And the standard deviation of these numbers, if you put them into the 5-point summary, you'll get a 0.29814. That would be your standard deviation. So that's what we're talking about. How does this mean, this U of P hat, compare to the population parameter P? Well, when we go back and look at the population parameter, it was 1/3. And then we took all the samples that we could and looked at the means of all the samples. We got 1/3. They matched exactly. That's important note. you can see that just by this little example, that if we use a sample, we can predict what the whole population is going to be. That's how we do some of the work we're going to be doing in statistics, okay? So U of p hat is equal to P. That's the way that works every single time, okay? Now, these are the formulas that are found on the formula chart. The mu of p hat, which is the mean of this particular sample, is equal to the mean, or to the entire population sample. And the standard deviation of p hat is equal to that percentage, that's p, times 1 minus that percentage, divided by n, and take the square root of it. That's what your standard deviation is going to be. So those are on the formula chart that you would use. And if you look on the formula chart that's at the end of every test, you should see it there, okay? So does the standard deviation of the sampling distribution equal the equation? So let's look at it. If we take 1/3 times 2/3, that's 1 minus p, and we take that, multiply those together, you're going to get 2 over 9 divided by 2. That's going to be equal to 1 over 9, and you take the square root of it, and you get 1/3. Is 1/3 equal to this 0.29814 like we calculated? Why? Well, there's a little bit of a correction we need to consider, because remember, we're talking about discrete situations, and these formulas here are considered continuous information. So we need to apply a little bit of a correction factor. And so that correction factor is found in the form of, I believe it's n minus your sample size, n minus over 9, x, the total population, minus 2, your sample size, divided by your total population minus 1. You take the square root of that. When you multiply this out, you get this 0.2981. That's what we calculated. That's why these two are slightly different. A little bit of a correction that we have to make. Okay? So, that's what we get right there. The total population minus the sample size divided by the total population minus 1. You take the square root of it. Okay. So just for rule of thumb just gets you in the general area. Your sample size must be less than 10% of the population to obtain independence. So in our situation there, we had 6 people. Did we have 10% less? Let's see, what's 10% of 6? It's less than 1. Well, you can't take a population of less than 1. That would be ridiculous. So can't take a sample that small. So we kind of fudged it a little bit, but that's the way you would typically do your sample size, okay? Has to be less than 10% of your total population to maintain independence. Your sample size must be large enough to ensure that you get a normal approximation. Well, what do you do there? You're looking at the number, your sample size, times the percentage, and that should be greater than 10, as well as the sample size times 1 minus that percentage should be greater than or equal to 10. This is the way you make certain that your sample size is big enough. This is the way you make certain it's small enough. Kind of gives you a range for your sample size. Okay? What does the second assumption assure an appropriate normal distribution? Well, suppose that n is equal to 10 and your probability is equal to 0.1, the probability of success. A histogram of this distribution is strongly skewed to the right. See it right here? Over here. Now use n equal 100 and p equal to 0.1. Now you take n times p and you get 10. Well, this histogram is still strongly skewed right. Look at what happens to the tail. It kind of all winds up being 0. But you can see it is a lot more normal in distribution. That's why we're looking at these type of distributions and why we say they have to be a certain size. Okay? Okay, move on. Based on past experience, a bank believes that 7% of its people who receive loans will not make payments on time. The bank recently approved 200 loans. What are the mean, standard deviation, and the proportion of clients in this group who may not make loans on time? Are our assumptions met? And what's the probability that over 10% of these clients will not make payments on time? Those are important questions to a bank, right? You would think so anyway. You'd hope it is. So first of all, the mu hat, it's at 0.07. Why? Because mu hat, the sample size, is going to be equal to the overall probability. And they said 7% in the past. We're going to live with that, 7%. We can find the standard deviation. 0.07 times 0.93 divided by 200, take the square root of it. You got a standard deviation of 0.018, nearly 0.02. So 80% of the people, 80% of these loans are going to fall between 0.05 and 0.09. Cool? So are the assumptions met? Well, what assumptions were you talking about? Well, sample size. If you take 0.07 times 200, you get 14, greater than 10. 0.93 times 200, and you get 186. Sample size is big enough for us to consider that our assumptions are going to be correct, and it's going to be a normal distribution. So you do a normal CDF of 0.1 and then some very large number, and 0.07 and this 0.018084, that's the standard deviation, and you're going to get this number here, 0.0482. So what do they say? They're saying that 4% of these clients will not make payments on time. Okay? Do I need to show you that on the calculator? Let's do that real quickly. Normal distribution, one of my least favorite ones. So we're doing a normal CDF, that'd be the second one right here. Okay, we're going to use 0.1 as our lower limit. We're going to use some upper number that's really, really, really huge. It doesn't matter what that upper limit number is at that point. Okay, we're going to use a mean of 0.07. We're going to use a standard deviation of, and I just need to move it over so I can see what that is, what that number was, because I don't have it memorized. 0.01804. Okay, and we hit enter and enter on that, and we hit enter and we get 0.048. So you can see where that's coming from. You can see how we're getting that information. Okay, let's move on. Suppose that one student tossed a coin 200 times and found that only 42% heads. Do you believe that this is likely to happen? Well, let's look at a couple of things here. What is our probability P? We know that P is going to be 0.5, right? He got 42% heads, so we're trying to see what's the probability that he got 42% heads. So we're looking at a binomial distribution there, right? So they're saying NP is 200 times 0.05. They're finding out sample size here. So 200 times 0.05 is 100. Big enough. 200 times 0.05 is going to be 1. So since they're both greater than 10, we can use a normal curve. We can find mu and standard deviation using our formulas. Okay? So they're saying that our mu is going to be 0.42. Our lower limit, some infinite number, we really don't care. Our normal percentage is 0.5, and we can find the standard deviation using this formula right here. So I want to actually key that one in and just show you that this does work, okay? So we do normal distribution. I'm sorry. Go ahead and do a normal CDF here. And our lower limit is going to be some negative number, some huge negative number. Doesn't matter what it is. So I just keyed in a bunch of 9s there. Okay. We're going to say our upper limit is 0.42, and then our mu is 0.5, and that our standard deviation in this situation is second square root of 0.5 times 0.5 divided by 200. And press enter on, or close your parenthesis there and press enter on this, and it comes up at 0.0118. So basically what this is saying is that if you look at a normal distribution curve like this, the percentage that's under the curve is somewhere like way down here. It's this little bitty percent down here. That's at 42% heads. Okay? And the area underneath this curve is 0.0118. So here's the question. That's 1% of the population. Do you believe that this is likely to happen? 1% of the time? Basically, you'd say no, since there's only a 1% chance of this happening. You don't believe this actually did happen. That would be kind of unusual for it to be really that low. That's where we're coming from. Assume that 30% of the students at TXVA wear contacts. If we sampled 100 students, what is the probability that we'll get more than 35% of them wearing contacts? And they want us to check our assumptions here. Well, let's see here. 0.3 times 100 is going to be 30, and 0.7 times 100 is going to be 70, and so sample size is large enough. Okay? No problems there. Our mu of piece of hat is going to be equal to 0.3. Our standard deviation in this situation is going to be equal to the square root of 0.3 times 0.7 divided by 100. And that's going to be equal to, I don't know, that's a point clear. Second standard deviation, I'm sorry, square root 0.3 times 0.7 divided by 100. And we get 0.458. There you go. That's our standard deviation. Okay? So, what do you think? What's the probability that that 35% of them wear contacts? Well, what are we looking at there? We're looking at P of X less than, more than, greater than, or equal to 35. So this is going to be a normal CDF. And we're going to be looking at some huge negative number, comma, 0.35, comma, 0.3, comma, and then 0.0458. So I'm going to bring up my distribution here. Second, normal distribution. I'm going to do a CDF. Huge negative number, 0.35, 0.3, and this one is going to be 0.0458. Enter, enter, and I wind up with a value of 86%. I think we got an 86% probability of getting there. And what I wound up with? I wound up looking at my normal curve, like this, and I said greater than this. So I actually looked at all of this area out here. We wanted this area over here. So if I wound up with that 0.86, I needed to do 1 minus that number, and I would wind up with 0.14. And that's where they got their number right here, approximately 0.14. Okay? Okay. So I do appreciate you guys letting me know that you're in AP statistics when it comes up. It really does help me find your information and respond to things quicker. I look forward to seeing you next time.